All right. So I believe we left off with the prime numbers last time. And what we'll do is just quickly go over some improvements that I made, slash some changes. Nothing major. Last time I forgot to add the ellipses to each of these stacks. Okay, as math operators. So just take a note of those quickly in the set of natural numbers and in the set of prime numbers here. Okay. And also I changed the HTML entity encoding for the double-struck capital indicators for each of the sets, from their numerical values to these values here. You'll notice the first letter is capitalized in each of them. And I haven't really dug too deeply into why these encodings are the way they are. I mean, obviously we have our capital P or capital N, and it's the same for pretty much the prefix matching the indicator for the set is the same for every letter. The list. So yeah, you can just Google this list of XML and HTML character entity references, and then you can go down. You can find these in a number of places, I'm sure, but it just happens to be where I found them. So you can find these boldface, or not boldface, but double struck for each of the letters of the alphabet. They're not all listed perfectly in order. You can see N is missing, but the encoding structure is the same, obviously. Okay, for the ones that are missing. So just wanted to point that out so that you can find those when you're typing up these code stacks. So let's just continue on with the prime numbers. A few more things to go over. Okay, and I guess I'll show what the objective is here. Okay, so we're going to go over just typing up some of this stuff here. All right, so let's just start with Axiom 1. It's our first axiom for this section. Okay, Axiom 1. Well, here's how we're going to do this. We're going to do these in two separate spans. One of them is going to be italicized, and the other is not. Okay? So font family, Latin Modern Roman. And font weight bold. Font style italicized. Italic. For the key term axiom. And then for this guy, all we need is font. Well, we need two things: font family Latin Modern Roman, and font weight bold. Okay. All right, so the idea here is that every not one natural number we'll use this expression here. So every not one natural number that is an element is either a prime number, or composite. Or composite. Okay. All right. So axiom 1, every not one natural number is either prime or composite. Okay. And then we will just state some context, namely that composite numbers may be factored as products of primes, as in okay, and then what I'm going to do is I'm not going to spend this whole I won't spend the whole video sort of going over the exact markup for this factorization tree. It's fairly straightforward in terms of what's entailed, though it might look somewhat intimidating. So we have a MathML expression here, and this is just a formalization of a factorization tree. Okay, so we have our MathML expression here above, which is fairly straightforward in terms of the markup. Okay, so for example, we see, I mean, again, just a regular setup for the actual markup itself. I use display absolute when I don't want the renderer to either do a sort of inline or a block manipulation. So I'm just using the expression display absolute because it essentially is treated as an escape character, so nothing happens, but it helps to control for the stack structure of the code. So, but yeah, so we have our leading expression here, math sub sup. Okay, so we have a subscript and a superscript for the particular leading term here. Okay, so what does that look like? Okay, so it's this guy. All right, and then I would like to use mfenched and Obsidian as well, but Obsidian has already deprecated the relevant code, I suppose, for rendering mfenced. So yeah, the math working group, the W3C math working group, considers MathML or mathfence obsolete anyhow, so we'll just have to contend with that make do with that fact whenever we're doing MathML in Obsidian. So just making a couple observations here. You'll find this document in my GitHub as well, so feel free to play around with it and reach out to me if you have any questions regarding the way in which I specifically code up this factorization tree. Okay, so but there you have it. And then also I'll just make the quick observation, or I'll just point out that if you want to play around with factorization trees in general, Wolfram demonstration project has this neat little tool here where you can sort of do different, you can sort of play around with different, worked fine, presumably. There you go. Okay, so here we have 2 raised to the power 4 times 7 would be the prime factorization for 112. So feel free to, it's always sort of like look for different Wolfram tools that might be relevant to what we're doing. Okay, so back to our current problem set. So here we have a generalization of a prime factorization tree. Okay, very good. And then next, we have our theorem expressed. So next, or our axiom rather. And then next we'll go ahead and write out the fundamental theorem of arithmetic. One tag at a time, I suppose. Okay, so and then let's go ahead and grab, while we're at it, grab this guy as well. Okay. And then what are we working with here? A theorem, fundamental theorem of arithmetic. In fact. So theorem 1, great. And now that we have a good amount of these CSS stylings worked out, we can just copy and paste and adjust as we need to. So fundamental fundamental theorem of arithmetic. Great. So the fundamental theorem of arithmetic states that every natural number has a unique prime factorization. And in our minds, we just might add the notion of up to the order of their primes. Okay, so I think I've commented on this before, but again, it's just basically the idea is that prime factorization is unique up to the ordering of these primes. Okay, so we might have some sort of permutation. We might have a variety of permutations of these particular factors, but they are essentially, the factorization is otherwise unique. Okay, for each particular composite or prime number for that matter. Great. Okay, and then let's give a definition. Okay, so that pretty much concludes. For now what we want to cover with regards to the prime numbers. So I definitely encourage everyone to play around with how to use MathML, okay, just as I've done here, and scalar vector graphics. Scalar vector graphics are the language or dialect used here to create the lines for the diagram. Okay, the edges. And this arrow here is, as you can see, where's my arrow? Yeah, so that's just a pure. That's actually a character encode. That's actually a special character that you can just find on your Mac pretty easily in this arrows list somewhere. I believe it's just so it's this guy probably, and then just a font variation. I believe I used that one. So pretty easy to find that guy. And I do a bit of font size manipulation on that guy. Okay, so everything else, it should be pretty straightforward to figure out for this prime factorization tree. So go ahead and play with that. And yeah, so that covers our needs for the prime numbers for the time being. Let's move on to the concept of zero. And the whole numbers. Okay. And let's just start out with the general sort of context again for zero and the whole numbers. So if we add the number, or concept really, 0 to the set of natural numbers, we obtain a new set of numbers which are called the whole numbers. And again, I'll just go ahead and conveniently copy my CSS styling. All right. And let's give the definition. So, right. That's easy enough. Definition 3. Okay. Set of whole numbers. This is sort of the beauty of modern day markdown and markup. Okay, so the set of whole numbers. And how would we define it? Using a bit of LaTeX. MathBB, Math bold anyway. Boldface W. And our set definition. So the set of whole numbers is obviously just 0 and the natural numbers. Lower, must have missed a comma in here. Okay, and our lower dots are ellipses. So we've got that. Now before we work on a bit of MathML markup for the whole numbers, let's just add a second axiom with regards to 0 that we're familiar with, of course. Okay, so what we'll do here is just go and grab our markup for the set of axioms, for the key term, I suppose, axiom. Grab the markup for the enumerator, 2, Okay, so axiom 2. Okay, so what we're going to use as an axiom 2 as the second given is just the fact that division by 0 is undefined. Okay? And we could, of course, do this as one expression, but the fact of the matter is that we have to work with the rendering engine here a little bit. I've sort of discovered that in preparing for this. So here we'll go. Okay, so we need v dash here. All right, for return style. And you guys, what I'm doing here is basically, what I mean here is just that by using lorem ipsum, okay, a fragment of lorem ipsum, is just the idea that division by 0 maps to, okay, so division by 0 maps to something meaningless, lorem ipsum. Okay, so let's see what that looks like. Okay, so that's good enough. Yeah, so again, the idea here is simply axiom 2, division by 0 yields or maps to something meaningless. In the print industry and otherwise, generally considered to represent something meaningless. Just a placeholder, just an empty placeholder, but in this case we're using it to mean senseless or something meaningless. Okay. And then let's just state that we consider it a self-evident fact that division by 0 is meaningless, and therefore undefined. Okay, so this is a familiar treatment, sort of formal motivation of the idea of the whole numbers, which includes the concept of 0, even though we refer to 0 oftentimes as a number, but let's just bear in mind that 0 is really more of a concept in the same way that infinity is more of a concept than it is a number. All right. So now we can just work out code structure. We can just copy either of our previous stacks. Okay. And put it inside a code block. Just like this. And make the relevant adjustments. So what are we dealing with here? We're dealing with the set of whole numbers. Okay, so whole numbers like we said before, these are semantic fields. Okay, so sharp S is used to indicate, in this case, a semantic space or a semantic field. Okay, it's a namespace right here. So we'll use that instead of the escape character. Sharp S. Okay. So far, so good. And then all that's left is to update the actual elements of the set here. So all we have to do here is, okay, yeah, then I'm just noticing that I ought to include, just as I stated at the outset, the ellipses for each of these set indicators here, right? Just to make sure that we're being consistent. So for this particular, all right. It's a functor, right? And separator false. Okay, good. All right, so back to updating our actual set here. And we can make some adjustments. Okay, so basically the semantic field for 0 just includes some names, some name variants, and of course a set membership. So that should be fine. All right, so and then we'll go 1. Excuse me. We'll add the idea of 0 factorial. The notion of 0 factorial. And for 2, I think we're good there. And then we have our ellipses. So that should do it. So, okay. And the last thing to do is just obviously correct this title here. So apologies for that little oversight. The whole numbers. I guess I used prime numbers and composite numbers. Gave a bit of context, namely that composite numbers can be factors as product of primes. Talk a little bit about sort of this general idea of a factorization tree. Introduce the fundamental theorem of arithmetic, which is a bit more of a formal statement of what's going on up here. And then we introduced a set of whole numbers via the notion of 0. Okay? Using a bit of LaTeX and MathML. So yeah, if you have any questions regarding anything that we've covered, by all means comment in the comment section below. I'll definitely make sure to keep my eye on the comment section, and also feel free to shoot me an email or reach out via GitHub or something like that. See you in the next one.